Okay, the next section, 4.8, we are covering this immediately following 4.1 because Newton's method is an application of linearization. So we're not going to wait till the end to do it. We are going to do it right after covering linearization to see a concrete application of it. So, example 1. We're given this polynomial function, x cubed minus 2. We're going to pick a whole number. Just for convenience, doesn't have to be a whole number, but just to make it easy, we're going to pick a whole number. And we are going to go ahead and sketch the tangent line 2f at this whole number. So we're going to start with our initial value, x naught. Our first value is going to be negative 2. So at negative 2, I'm going to label, there's our x naught. If we go all the way down, we get right here, and I'm going to draw the equation of the tangent line to the best of my ability, which looks something like that. Okay, and I'm going to call this tangent line L0 because it corresponds to x0. It's the tangent line 2f at x0. So now, wherever this line crosses the x-axis, that intercept right there, that gives us our next x value. So this tangent line is guaranteed to cross the x-axis at least someplace, provided that the tangent line at this point is not horizontal. So for instance, right here, the tangent line is this, it's horizontal, it's never going to cross the x-axis because they're parallel. So provided the first derivative of our function f at our value is not 0, then this process works. So, the tangent line certainly is not 0. Is not horizontal. Has a positive slope. It intersects the x-axis right here. Provides us with our next x value. If we follow that down to the graph, we get something like this point, and at this location, to the best of my ability, which is sometimes not great at drawing. There we go. Draw the second one. It's harder than it looks to draw a straight line. So we're going to call this line L1. It's going to cross right here, and this is x2. And again, we follow it down. We get a point on here, and at this location, we're going to sketch the tangent line here. This one's going to be even harder to do. There we go. Not bad. Okay. Might be going uphill a little bit more than it should, but you get the idea. There we go. So then this value right here, x3, is our next value. So then if we go ahead and follow this down, we'll get this point, and the tangent line there looks something like this. So hold on, let me label the last line. This was the this is the L3 tangent line. Oh, sorry, no, this is the L2 tangent line. This is the L3 tangent line, for a total of 4 tangent lines. First x value, right here, tangent line, crosses right here, form the tangent line there. This intercept, form the tangent line there, produces this intercept, form this tangent line, and it gives us this intercept right here, which I will label. Now, the overall trend here that we should see is that these values, x0, x1, x2, x3, x4, they all seem to be getting closer to this intercept. So, if this process were to continue, that is, as I goes to infinity, where does xi go? So I will go ahead and claim that the limit as I goes to infinity of xi is going to be the x-intercept. And in this case, the x-intercept is whenever x cubed minus 2 equals 0, which is the cube root of 2. So in this case, it would be the cube root of 2. So Newton's method uses the linearization of a function, in other words, a tangent line, as a way to figure out when a graph crosses the x-axis. To figure out, in other words, when does f of x equal 0? We can use Newton's method to solve that.